and he's going to talk about that, about all that.
And all that. So thanks to the organizers for inviting me here. It's been a wonderful conference. I want to discuss a couple of things, but particularly try to get to some phenomenology that you get from these heterotic models. But let me just review the model, and I also want to add something that's only a few days old to this, which I think is of interest. In any case, as is well known, we're going to start off with E8 cross E8 heterotic string, and we're going to compactify on a Calabi-Yau down to 4 dimensions. Calabi-Yau will geometrically preserve n equals 1, but we're going to put a vector bundle as well for the gauge field. I'm going to choose SU4 structure group. We're going to make sure that the vector bundle is slope stable with 0 slope, and that will also preserve n equal 1 supersymmetry. We can compute the exact content of matter and conjugate matter, Higgs and moduli, using sheaf cohomology, the output of a couple of years of the Penn math physics group. And if we do this, we get the following theory. The gauge group, SU4, breaks this down, of course, to spin 10. We have Z3 cross Z3 Wilson lines. I forgot to say that, but we're going to work on Calabi-Yaus that have a non-trivial homotopy in our case. And that turns out the simplest one to do is Z3 cross Z3. And this was work with these people in 2006, but I'm going to extend it significantly in a moment. Here are our Wilson lines associated with B minus L and hypercharge. And when you turn on the Wilson lines, they're embedded in the E8, and they spontaneously break spin 10 down to the standard model in this case with an extra gauge group, because you have to preserve the rank. And that extra gauge group is just gauge B minus L. It's an interesting fact. It's an interesting simple extension of the standard model. If you have right-handed neutrinos, which these models will have, and perhaps we have in nature, seems so, then in fact you can always gauge B minus L and get an extra U1 B minus L anomaly-free group. So in some sense, it's the simplest extension of the standard model you could ever imagine. Right-handed neutrinos and just gauge B minus L. In any case, that's exactly what you get when you use Wilson lines to break down spin 10 and choose the Wilson lines in this way. You can exactly, using sheaf cohomology, compute the spectrum. We do this on a covering space, but then we mod out to a quotient group. So what you have to do is compute the, stopped working. Oops, got my fingers in the way. Sheaf cohomology times the representation, spin 10 representation, and take the Z3 cross Z3 invariant part. And when you do all of that, we found that we got exactly 3 families of quarks and leptons in standard representations, including right-handed neutrinos, 1 per family, and exactly 1 pair of Higgs and Higgs bar and nothing else, with no exotics whatsoever, no vector-like pairs. This is exactly the MSSM spectrum with right-handed neutrinos. You also get a few vector bundle moduli. In this case, it's rather limited. We only have 13 of them. A new thing that I want to discuss here today, which is only a week or so old, is that when we first did these models, we always used anti-branes to solve the anomaly condition, because we wanted to use anti-branes. We were doing KKLT, and we wanted to break supersymmetry that way and lift the potential so that it could have a small cosmological constant. But if you want to get a completely supersymmetric theory, then I will show you how to go about finding a hidden sector that will do that as well. But before discussing that hidden sector, I have to be a little bit more explicit about which Calabi-Yau we're talking about and which vector bundle we're talking about that's on it. So the Calabi-Yau has H11 equals 3, so the 1-1 cohomology space is 3-dimensional, and its span will pick some basis. There's a particular basis we find most interesting, tau 1, tau 2, and phi. The Kähler cone is the positive octant in that space. So it's an SU4 bundle, so it'll immediately have vanishing first Chern class and hence vanishing slope, but that doesn't make it slope stable. So you have to check that every single sub-bundle has slope that's strictly less than 0. And that is a long job, And when you do it, you get a zillion different inequalities, but in fact, they reduce down to the following rather simpler set of inequalities in the Kähler moduli space. So the bottom line is this. This is some crazy spherical projection along the radii, which I won't try to explain further. And what you find is that within this teardrop region, for any modulus within that teardrop region, you satisfy all of these constraints. The bundle's slope stable with zero slope, so you preserve supersymmetry. And I'll come back to this later, but we want to be within this region of Kähler moduli space whenever we're discussing anything so that we preserve supersymmetry in the bundle in the observable sector. So what is this new hidden sector going to be? Well, it's very simple. Here we have our Calabi-Yau. It's still got holes in it, but we're not going to wrap any Wilson lines on here. And in fact, this is all based on work. Well, I'll discuss that in a second. So what are we going to do here? Well, we should put a bundle on here as well. We're going to do something very simple. We're going to take a line bundle. Structure group is just U1, and the bundle will be given, essentially, they're categorized by the first Chern class, and so the L1, L2, and L3 will be the coefficients of tau 1, tau 2, and phi. We want to admit spinners, so in fact, to get vanishing Stiefel-Whitney class, we take these guys to be even. Also, this should be equivariant because everything's coming down here from a covering space with the Z3 cross Z3 action on it. So these things, L1 and L2, have to be 0 mod 3 so that this descends from an equivariant bundle. So we have to satisfy a bunch of conditions on L. First one, we want to satisfy the anomaly condition. So we now have a Chern character sitting here rather than a Chern class. But otherwise, we have the C2 on the observable sector, the Calabi-Yau C2. We are allowing for 5 branes, with at least in this example, we will need. And then we have the line bundle. So that is anomaly cancellation. Then there are D terms associated with the U1, this particular U1. And at tree level, you just get this first Chern class JJ. However, there are corrections to this. And these corrections, I'll discuss that almost in a moment, but these corrections are very important. They depend on the line bundle, they depend on the 5 branes. There's a coefficient in them, which is actually given by this particular trace. And this thing is the phi A Iliopolis term, appropriately corrected. And what we'd like to do is set that to be 0 so the D term will vanish. It could also be canceled by vacuum expectation values of charged fields, but I won't discuss that here. I'll assume, and there are models in which that's true, in which these VEVs vanish, so you would have to set the phi Iliopolis term to 0. The same thing is going to be true. We have to check 4 pi over g squared, both in the observable and hidden sector. These have threshold corrections, and I have to make sure that these things are positive when you do all of this, put it all together. So our work is very much based on papers. First one was Blumenhagen, Honecker, and Weigand, Timo's thesis, and then a lot of other papers with these authors and some others. And they introduced such correction terms, including DUY, in particular limits, particularly where the radius of the 11th dimension is less than that of the Calabi-Yau. Strong coupling, but in that limit. However, myself with Lucas and Waldrum, all the way back in our classic papers on heterotic M theory, actually have derived exactly the same things as kappa 4/3 extensions, the kappa 4/3 level of strongly coupled M theory. And it is gratifying to find that when you get the notation right eventually, that they're exactly identical. So we're going to use these formulas everywhere. And so we have to solve all of those things. We have to embed the U1 and E8. I'm going to embed it in this talk in the following way. There's a maximal subgroup SU2 cross E7. I'll embed the U1 and the SU2 with that particular diagonal generator. And if you do that, you'll find that coefficient little a is equal to 1. You have to get the correct 4-dimension G Newton and also alpha gut. I'm going to take G of S to be 20, which lies somewhat in this regime. I'm just taking it as an example. There's a lot more physics that we have to do with this, but you can adjust this so that that works out well. We solve all these equations and we get many solutions. One of them is, let's say, a line bundle is just 242. However, that may be the line bundle, but it's only valid over a certain regime of moduli space, and it's a long story too, but this red blob is the region which satisfies all of the equations. Anomaly, G squared is positive. The DUY equation equals 0. However, it had better overlap the region in which the visible sector bundle is also stable, and it does, because this region corresponds to where that teardrop in which that was stable. So we can get this whole thing to work. What is the theory on the hidden sector in this case? Well, the U1 breaks the E8 to U1 anomalous cross E7. And then we have a spectrum we can compute with the cohomology. And what we find is that we get some charged matter, 26 of these, but the minus charge guy doesn't appear. And we get some more charged matter here, but the minus charge doesn't appear. It's truly anomalous. It satisfies all those equations, and so on and so on. So it is possible, very easily possible, to get supersymmetric extensions of these heterotic standard models. So the fact that we gave them with anti-branes, if you want to do models that are completely supersymmetric, that's how it goes. Okay, so what I'd like to do is analyze this, what I'll call the B minus L MSSM, which is this original theory on the observable sector, which has this extra gauge B minus L. The original generators were these. However, if you use these, you will get initial operator mixing, and furthermore, you will get operator mixing as you evolve. The two F mu nus can mix together, and that creates havoc in trying to solve the low energy theory. So the question we asked ourselves was, is there some other basis that one can choose so that there's absolutely no kinetic mixing at all? The answer is yes. It's a long story which I cannot discuss here, but I'll just tell you the answer. If you use B minus L again, but the diagonal part of an SU2 right, then it turns out that everything works out beautifully, as I will show you. First, you have to check that these also have the correct spectrum, and it does have the correct spectrum. Other choices of Wilson lines do not give you the MSSM and with various problems and so on, but this one also gives you correct MSSM. So what about operator mixing, kinetic mixing? Well, for arbitrary U1, U2, the problem is that you can get this F1, F2 mixing. If I take U1 to be T3 right and B minus L, the things I showed a moment ago, and just use the standard normalization, then the killing brackets of these particular new generators, they're orthogonal to each other. So there's no initial mixing at all. However, as you scale down, you have to worry about it. General for U1 cross U1, you have mixing. You have the covariant derivative, which is diagonal. However, you can scale away by rotations and rescaling. You can make it such that there is no kinetic mixing, but then the covariant derivative gets a mixing. It just never goes away. So we have to deal with this mixing here. We'd like it to vanish. So what happens with that particular G of M? It will vanish at the initial condition, as I just said, but it has a renormalization group. The renormalization group beta function contains itself, this G of M, for the first 4 terms. So if 0 to begin with, it stays 0. However, the last term does not have that, and there's an inhomogeneous term without G of M, and this can cause it to regrow as you scale. That B is just this Bij given by this particular object, where you trace over the low energy gauge group, over the low energy gauge multiplets. And say it again, low energy multiplets. G of m is 0 initially, but it can regrow, so it's only when this trace over the low energy multiplets is 0 that you won't regrow operator mixing. And generically, that's absolutely not the case, but if we try this out for our canonical basis, we find that, in fact, it's true over the full representations that fill out the 16, of course, because it was true at spin 10. But we have natural projection of color triplet Higgs. They're gone. So we only have doublets. And then you have to check that if you compute this thing over the Higgs doublets, you also get 0, and you do. So the fact is that you have absolutely no mixing either initially, nor will it regrow in the course of time. And so this really helps because you can now do a very detailed renormalization group analysis of this thing. It's true in today's age of computers, you can do anything you want, but it's nice to have analytic expressions for a lot of things. So this basis we find very interesting, this canonical basis. You could ask yourself, well, maybe there's a lot of other bases that have just a similar effect, but it's not true. You can prove a theorem which says that the only basis up to some multiples, in the Lie algebra, the only basis that doesn't have kinetic mixing at all is this canonical basis. It wasn't true in the hypercharged B minus L basis. It caused us a lot of troubles, but it is true here. So that's a nice part. So I'd like to deal with this particular model. We're going to work with that basis. We have exactly the MSSM. We can do a very complete renormalization group analysis of this. And I'd like to discuss various aspects of that heading toward low energy predictions. And one thing I'd like to talk about is sequential Wilson line breaking. This is actually an interesting thing. It's a difficult issue, but I will point out that the first homotopy of our particular model is Z3 cross Z3, as I've said, and there is absolutely no reason. There's two independent classes of non-contractible curves, and there's absolutely no reason why each one has to have the same radius where you wrap over these things. The Calabi-Yau, as it moves in its moduli space, can distort. It can be more spherical, more distorted, and so on. So I want to ask myself, what happens when you have some distortion and the Wilson lines are not the same? So I'll denote the masses of each Wilson line, the T3 Wilson line and the B minus L Wilson line, to be the inverse of the radius over which it wraps. Now, if you think geometrically about that, that's a long story as to what that means. I can tell you a little about that as I go. But in any case, that you can imagine that each Wilson line has a mass scale associated with it. And there are three possibilities. These are approximately the same, which is what we usually do. But you could also imagine that there's some splitting, that the B minus L Wilson line has a larger mass than the T3 right, or vice versa. And just depends how you distort the Calabi-Yau. The effect of this is rather dramatic, even if you do small distortions. So I want to discuss this a little bit with you. So let's say that the B minus L is larger than the T3 right. So we will recall what this B minus L was. It's just simply, for normalization regions, 3 times B minus L. That cubes to 1, so it's a good Wilson line. It was set up to commute with SU3 cross SU2 by definition, but it also commutes with the alpha 5 in the Dinkin diagram. So it actually, it commutes with SU2 right as well. So if you ask what the commutant just of that Wilson line is, the spin 10 goes into SU3, SU2 cross SU2 right cross U1 B minus L. In other words, you get the gauge group of the left-right model. Okay. Now, as you scale down the T3 right, you'll hit a mass where it turns on. And when it turns on, it breaks the SU2 right down to its diagonal subgroup, which is this U1 T3 right, and then we continue with what I was talking about before. So there's some intermediate region between where the Wilson lines turn on and the second one turns on that we have to deal with. Yes?
As far as I understood before, your modernized space is already kind of confined. Yeah, so you cannot really tune so much your radii anymore. So how did these masses depend on your model line that you have?
Yeah, so it's a long story which I can't begin, but we can look at that. There's a lot of issues. Let me just mention in advance. One of them is I have to worry about Kaluza-Klein modes when I do this as well. The amount of distortion I'm going to talk about is relatively small. And for the relatively small distortion, and I'll show you why it's relatively small. Yeah, I'm going to have to keep going here. You will find that that we can fit all of this together, is the answer. In any case, if I do that, I get a left-right model. However, if I did the other way around, T3 before B minus L, then I look at the other generator and I ask what that commutes with. It's SU3, SU2, but it also commutes with this extension of the Dinkin diagram. It's an SU4. So actually, if you turn on that Wilson line, you break down to SU4, I'll call SU4 color, cross SU2 left, and U1 T3 right. That's the Putty-Salam gauge group. And then again, when you hit the intermediate coupling, you get the low energy theory, the MSSM, the B minus L MSSM I was talking about before. Because at that scale, SU4 breaks to SU3 cross U1 B minus L. We can exactly compute the zero modes in each of these regions using this technology of sheaf cohomology. And when you do that, you get the following thing. If you go through a left-right model, then through this intermediate regime, you end up with exactly this spectrum, so we know what the beta functions are there. And then you break this down with this Wilson line down to this B minus L MSSM. Or you can go through a Putty-Salam gauge group, but you get exactly this spectrum. These aren't the normal spectra you get. And then when the second Wilson line turns on, it breaks it down further. Now you will worry about Kaluza-Klein modes in here. Long story, which I can't discuss here. I will simply say we have worried about it. You never have more than one Kaluza-Klein mode here because the mass gap is relatively large. You do have it, but it's in mid-threshold. So its effect on the beta function compared to the explicit zero modes is suppressed. So using these beta functions in this intermediate regime is a good approximation, we find. Okay. So what's the story here? We have in these models generically an extra, it's a T3 right B minus L, and we have to break it down to hypercharge. How do you do that? So we have to break this thing down below the intermediate scale. How does that get done? Well, when you have the U1 cross U1 theory at low, you have this particular covariant derivative. G of M vanishes because nothing mixes, so we just have the W associated with T3 right and the B minus L W. And we look at the potential for the right-handed neutrino. The only particle here that carries these quantum numbers but doesn't carry any of the rest of the standard model quantum numbers is each one of the right-handed neutrinos. I'll pick one of them because I can't discuss the whole story here. There's a complicated Lagrangian. However, all of them are small because the Yukawa parameters of right-handed neutrinos are tiny. So this is the dominant terms. And what we find is that if you start off with a positive soft mass squared for the right-handed neutrino, it can in fact be driven negative and turn over and spontaneously break the theory. In fact, here's an explicit example of this thing. Because there's no operator mixing, I can actually write exact renormalization group equations for this and solve it analytically, which is extremely nice. I'm going to assume unification, which I'll justify in a second, and I will take some value for the unified gaugino mass. I'm going to take all soft masses to be universal, but I'll allow the first and second neutrino masses to vary a little bit. When they're all universal, then in fact the third family neutrino squared does not turn over. But as I begin to vary them, and not terribly much, by a factor of 3 say, Okay. Then, in fact, when you follow this down, you see that it does turn over. This is the mass squared of this neutrino, goes negative, and you spontaneously break these symmetries. So there is a beautiful way in which the right-handed neutrinos by themselves simply break this extra symmetry. So if you look at this and you say, oh, that's not the MSSM because it's got an extra B minus L in it, yes, but it is spontaneously broken very easily without fine-tuning at a lower scale. So the picture here is that we have some unification scale, an intermediate scale between where you may or may not turn on the second Wilson line. You have a left-right theory, a Patti-Salam theory, depending on which one turns on first. After M intermediate, you have a long range where this B minus L MSSM occurs. You then spontaneously break B minus L. That gives you hypercharge. This is the relation between the hypercharge and the 3 right and the B minus L coupling. You then go down further until you break supersymmetry. You start, which is, we will estimate as the square root of the left versus right stops. And then you go down further without supersymmetry, just standard model, down to the Z mass, where we put in the precision measures alpha 1, alpha 2, and alpha 3. So for example, of how this thing goes, this is just one possible example. If we set M SUSY to be a TEV and take B minus L to be a TEV, normally they're split, but I'll just give a simple example. Then we find that we can enforce exact unification at 3 times 10 to the 16th JeV. That just comes out of it by splitting this M intermediate. M intermediate is a factor of 8 below the first Wilson line. So the one Wilson line turns on B minus L, the other one turns on after it, less than one order of magnitude smaller. And we can run the parameters subject to all of the thresholds and everything else down there. And what you find is you get rather dramatic tuning of this to unify. You can do this in various ways, shapes, and forms. In fact, you don't have to split the moduli to tune this if the colored squarks were sufficiently heavy and not crazily so. You'll also get unification, but I don't have the time to discuss that here. So as a final transparency, what we're trying to do here is just compute the low energy LHC effects of a real string model. We have a theory, and yes, there are lots of things to talk about in the string theory, computing soft terms and whatever, stabilizing moduli and whatever. I won't discuss any of that here, so I'm not claiming this is perfectly known physics, but it's a reasonable idea. It's got exactly the right spectrum. You have a supersymmetric hidden sector if you wish, and so on and so on. When you scale this thing down, the extra U1 symmetry you get spontaneously breaks down, so the U1 cross U1 turns into hypercharge. So that works very nicely. When you work this all out, then you might ask yourself, well, what are we going to predict at low energy, let's say, for the particle spectrum? And we can do that. So it's a long story, and there's assumptions in here like universality of various classes of soft breaking terms and so on, which if anybody was interested, I can tell you. But at the end of the day, we end up plotting mu parameter against tan beta. This plot is a year and a few months old, so this should not be taken seriously as up to date, but it gives you an example. We're in the process of computing this up to date as we speak. This dark red region is a region where all bounds on squarks, leptons a year and 3 months ago were satisfied. So let me look at a line that cuts this, and let me pick throw a dart and you hit point Q, and I'd like to know what happens at point Q, which is allowed by everything else in the theory. First thing I'd like to know is what the hierarchy is between B minus L and electroweak physics. So here's that line. I'm moving along that line. This corresponds to the point Q. The hierarchy between the mass of the B minus L boson and the Z boson starts off at the bottom of this allowed region being about 14.5, And then as you approach this white region, in the white region, electroweak symmetry no longer is broken. There is a fine-tuning that takes place to make this thing work as you get closer and closer to it. No fine-tuning down here, or minimal. What Luis was talking about is it also acts in this region, but I won't discuss it now. If I don't want any fine-tuning, I should cut this off about here. So I would find a hierarchy, B minus L, electroweak hierarchy of between 14 and about 60 or 70, something like that. So these things are not really large. This breaking occurs relatively low, and you preserve B minus L down to a very low scale. We can compute every squark lepton and Higgs at Q, and here's the results that we got. Of course, the one I want to point to is the Higgs 0, the lightest neutral Higgs, and we got 127 GeV. Am I touting a prediction here, or something? This, remember, is a year and a few months old. The answer is no, because there's lots of input into this thing, and that Higgs wanders around. So we never got this Higgs to be bigger than about 135 GeV. There's a relation between it and the hierarchy and naturalness. But if you go through that, you find that you always end up in a region like this. And then, at least for me, it's extremely satisfying if CERN announces this Higgs in the region where they have it, because softly broken supersymmetry always leads to a region like that. In any case, we can compute all the other masses here, and one has to be careful. We've spontaneously broken B minus L here, so a lot of the bounds that you get for superpartners, a lot of them are strictly tied to MSSM with strict R parity, and we've broken R parity. So you have to look at this carefully, and through the course of the summer, I suspect we will. Thank you very much.
Okay, thank you very much for that. Questions?
Yes, I'm curious about the fact that you got a Higgs mass of 127 when you have light stops and you have the small tangent beta.
Yeah.
How is that possible?
Well, it's all possible because of the initial soft breaking parameter spectrum of this thing. So it is possible to do it, and it's just a matter of what your initial conditions were.
No, but it depends on the low energy conditions, right? The Higgs mass. So I don't understand how. But we can.
Well, yeah, we'll talk about it later. But no, but there's something that's different here, which is this: you have the extra B minus L spontaneously broken. This couples into everything.
That enters into the Higgs potential?
Yes, absolutely. In fact, all of these results are very much related to the fact that there's this B minus L, extra B minus L.
And let me ask a second question. You're going to have to raise, since your squarks and leptons are sort of degenerate with the gluino.
Yeah.
In that range of parameters, LHC seems to rule out gluino masses below 1.2 TeV.
Yeah.
How hard is it to raise everybody up?
Trivial, and that's the thing I hate about it. It's easy to raise everything up. First thing I want to say is, well, as you know, I'm no expert, and this phenomenology here really has to be done right, and I'm the wrong person to talk about it. But there's two comments. First of all, we break R parity, and so a lot of experimental results, in fact, have used R parity in their limits. So you have to be careful with that. People who know what they're talking about, be it Langacker or Barger or others, in fact, point this out all the time. It's very important. So I don't know how to take that, but let's say that that's so. Unfortunately, we have soft masses, which I do not know how to calculate it at the moment. And if you push these things up, these things move around quite a bit. Of course, there are these fine-tuning bounds that really matter here. So if you don't want to fine-tune, then you get stuck in a region. And we are attempting to do a more modern analysis of this as we speak.
Concerning your line bundle in the hidden sector, I have a confusion because so you have a line bundle that is supersymmetric, but it contributes like an anti-pipe. So there's a negative class for.
I'm sorry, say that again?
It contributes negatively to the tadpole, right? To turn 2.
Yeah, I guess so. It's got a C cubed in there somewhere. Yes.
So do you have a good intuition for that, how that can be? It's supersymmetric, but nonetheless it has a negative contribution there?
Yeah, well, it's what requires supersymmetry is that phi Heliopolis term vanish. And so as long as it does vanish, I do have supersymmetry. And so the question you have to ask is whether you can, within a complete set of moduli that don't ruin other things, solve the DUI equation. And the answer is you can. That's the best I can say. And in fact, it almost gets trivial at some point because there really are light states, charged light states associated with this. And when you work them out, which I showed you there briefly, they come out with precisely the sign so that were that equation to start becoming slightly negative, their vevs could cancel it. So you actually have a fairly large region of moduli space where you can, in fact, set the phi Heliopolis to 0 and get supersymmetry.
There's a tension here between your Z prime mass just from direct limits and proton stability, right? Because you're breaking R parity and there's nothing else protecting your proton mass, your proton stability. So can you comment on that at all?
Yeah, so proton stability goes away from, we're starting off with B minus L, so you get rid of LLE terms and the UUD term, you don't have any proton decay. What you grow back, because it's a right-handed neutrino, what you end up growing back is the LLE term. You don't grow back, it's a lepton. So you really break lepton number. So the LLE piece grows back, but you don't break baryon number because it's a right-handed neutrino. So that doesn't immediately grow back and it's naturally suppressed. So what you tend to get is a somewhat naturally suppressed proton decay from that reason alone. So it's the right-handed neutrino that does it. However, in addition to that, there is the Yukawa coupling from the right-handed neutrinos, and they enter that, and they have to be taken sufficiently small to make the proton decay sufficiently slowly. And that's something like 10 to the minus 8 or something like that will make that work. That's how it works. So you can get good proton decay. It's quasi-natural, but you need a small Yukawa coupling for right-handed neutrinos.
So I'm just confused about Timo's point too. So you're making the statement that you can have a small instanton transition where you absorb an anti-M5 and preserve supersymmetry. That's the statement.
I'm not doing a small instanton transition. I don't understand. I'm just putting a bundle on the hidden sector. I'm not doing a transition there. I have a 5 brain in the bulk, which I didn't discuss much about, but that's not making a transition. It's just stable at some point in the bulk, which turns out to be 0.32 something, and you can move these things around. All you have to do, the supersymmetry is encoded in the phi Heliopolis term. If you assume there's no vevs of charged states, then the phi Heliopolis term should vanish, and you can make it vanish with G squareds being positive and all the other things that you need in a restricted region of moduli space. And you might ask whether that's possible, and the attempt of my red and blue graph was to show that it is.
Does that mean your corrections to Donaldson-Uhlenbeck-Yau are fairly large? Because in the Donaldson-Uhlenbeck-Yau case, you can't have, I mean, this is, I guess, Timo's question. You can't have this negative C2.
Yeah, so I think, I'm never quite sure how to say this. I'm not changing Donaldson-Uhlenbeck and Yau at all. Not in the slightest. It's just that the phi Heliopolis term of a U1 D term actually gets threshold corrections. And all I want to do is set the D term to 0. I couldn't care less about anything else. So I'm not relying on any theorem of Donaldson, Uhlenbeck, and Yau at all. Were you to ask me what the tree level slope, Donaldson, Uhlenbeck, Yau slope of a line bundle is, it's positive. But it can be canceled by these threshold corrections, and that's what we're doing. There is this attempt to go to lambda stability associated with pi stability, And at least from my point of view, this is not necessary to look at some new kind of stability beyond Donaldson-Uhlenbeck. Yao, slope stability. You can use their thing, just have to remember that it was only a tree level effect. If there's no line bundles, there are no issues.
Yeah, just to comment that I think there's no contradiction between those two viewpoints. The correction term in the Fayolopoulos term takes into account the warping across this 11th dimension. So if you actually look at the slope in terms of the Kähler parameters on the boundary, that's exactly the same as the D term.
Yeah,
So the Donaldson-Uhlenbeck and Yao picture and the D term picture are exactly the same if you take that warping into account.
yeah, I agree with that. I just found you don't have to think that way in order to understand this. It's just setting a D term, a phi Heliopolis D term to 0.
Okay, so we better move on. Thank you very much again.